Chapter 7, Module 2. The purpose of this module is to discuss two most important properties of covering projections. One is the path lifting property and the second one is the homotopy lifting property. We have already proved earlier these properties for exponential map, but now we shall discuss these properties for any covering projection from any arbitrary topological space x tilde to any arbitrary topological space x. For proving uniqueness of path lifting property of covering map, we need the following lemmas. Suppose Y is a topological space and P from x tilde to x is any covering map. If f and g are two continuous functions such that P composed f is equal to P composed g, that means the diagram shown here commutes, then the set S consisting of all the points a from y with the property that f a equal to g a is a Clopin subset of y. So, for proving that S is open, we choose any point x from S, then f x and g x are same in x tilde. So, P of f x equal to P of g x, which implies P composed f x equal to P composed g x in capital X. By definition of a covering map, there exists a neighborhood u of P of f x such that P inverse u is the disjoint union of V alphas, where V alpha is open in x tilde and homeomorphic to u by the restriction of P. Then f x equal to g x belonging to V beta for some beta, that is x belongs to the intersection of the sets f inverse V beta and g inverse V beta. Since f and g are continuous, f inverse V beta and g inverse V beta are open in Y. Consequently, we get an open neighborhood f inverse V beta intersection g inverse V beta of x in capital Y. We claim that this intersection is a subset of S. If I take a point y from f inverse V beta intersection g inverse V beta, then y belongs to f inverse V beta as well as y belongs to g inverse V beta. So, both the points f y and g y are in V beta. Since P restricted to V beta is a homeomorphism and it is known that P of f y is equal to P of g y, we get f y equal to g y. Therefore, the point y becomes a member of capital S. That means, between x and S we can insert the open set f inverse V beta intersection g inverse V beta. So, S becomes a neighborhood of each of its points, that is S is open. Now, we are to show that S is a closed set in Y. If possible, let us take a point B from S bar minus S, then F B and G B are two different points, but P of F B is equal to P of G B in capital X. Let W be an admissible open neighborhood of P of F B and the collection V alpha form a partition of P inverse W. We claim that there exists alpha not equal to beta such that F B is in V alpha and G B is in V beta. If not, then both F B and G B are points in V gamma with P of F B is equal to P of G B, which implies that F B is equal to G B, because the restriction of P on V gamma is a homeomorphism of V gamma onto W. So, the point B is in the intersection F inverse V alpha intersection G inverse V beta. By continuity of F and G, we get that F inverse V alpha intersection G inverse V beta is an open neighborhood of B in Y. As B is in the set S bar minus S, F inverse V alpha intersection G inverse V beta intersection with S is non-empty. Choose a point from this intersection, then F of A is in V alpha, G of A is in V beta, and F A and G A have the same value. Hence, V alpha intersection V beta is not equal to phi, which gives a contradiction. Consequently, S bar is equal to S, proving that S is a closed set. Now, we state the next lemma. Let P from x tilde to x be a covering map and Y a connected space. If G1, G2 are functions from Y to x tilde and F from Y to x all are continuous such that P compose G1 is equal to F equal to P compose G2, and there exists a point y0 in capital Y such that G1 y0 equal to G2 y0, then both G1 and G2 are same. Now, we take capital S as the collection of all points A from Y such that G1A equal to G2A. By the previous lemma, S must be a clopin set in Y. Now, since G1 y0 equal to G2 y0 for some y0 belonging to capital Y, we must have y0 a member of the set S. That means the set S is non-empty. Since Y is connected and S is a non-empty clopin subset of Y, S must be equal to Y. Hence, G1 is equal to G2. Now, we state the theorem, what we call path lifting property of covering map. Let P be a covering map from x tilde to x and alpha a path beginning at some point x0 of capital X. Given any point x0 tilde of x tilde with the property that P of x0 tilde equal to x0, there exists a unique path alpha tilde starting at x0 tilde such that P composed alpha tilde equal to alpha. This alpha tilde is called a lift of alpha. Since alpha is a continuous function and I is connected, alpha I is a connected subset of capital X. There are two possibilities. The first one is that alpha I is contained in some admissible open neighborhood U of x, or alpha I is not contained in a single admissible neighborhood of capital X. So, let us discuss the first case when alpha I is contained in some admissible open neighborhood U of x. P inverse U is union of disjoint open sets V beta such that each V beta is homeomorphic to U by P. Choose any V beta and consider alpha tilde as the function, the composite of inverse of P restricted to V beta with alpha. Then alpha tilde is a continuous function such that P composed alpha tilde is alpha, and alpha tilde evaluated at the point 0 is x0 tilde. That means alpha tilde is a lift of alpha. Now, in the case 2, if we consider that alpha I is not contained in a single admissible neighborhood of x, then we choose an open cover V beta of capital X by admissible open neighborhoods of x. Then the collection alpha inverse V beta is an open cover of capital I. Since I is compact, this open cover has a Lebesgue number. Let us call that Lebesgue number epsilon. Now, we choose a partition of the closed interval 0, 1 by the points T I such that the length of each subinterval T I to T I plus 1 is less than or equal to epsilon. Then the image of this subinterval T I to T I plus 1 by the map alpha is contained in some admissible open neighborhood V I plus 1 for every I from 0 to n minus 1. Now, let U1 be the path component of P inverse V1 such that x0 tilde is a point in U1. We define a function alpha 0 tilde on the subinterval T0 to T1 by the formula that it is the composite of P restricted to U1 inverse with alpha. Then alpha 0 tilde is a continuous function such that P composed alpha 0 tilde is equal to alpha in the subinterval T0 to T1, and alpha 0 tilde evaluated at the point 0 is x0 tilde. So, alpha 0 tilde is a lift of alpha restricted to T0 to T1. Now, assume that alpha bar is already defined on the closed interval T0 to Tk for every k greater than 1 such that alpha bar is a lift of alpha restricted to the closed interval T0 to Tk. Then alpha of the subinterval Tk to Tk plus 1 is contained in Vk plus 1. Now, we choose a path component Uk plus 1 of P inverse Vk plus 1 such that Uk plus 1 contains alpha bar Tk. Since P restricted to Uk plus 1 is a homeomorphism, we define an extension alpha tilde of alpha bar by the formula that P restricted to Uk plus 1 inverse composed alpha of T is equal to alpha tilde T for all T belonging to the subinterval Tk to Tk plus 1. Then alpha tilde is a path in x tilde defined on the closed interval I which lifts alpha restricted to T0 to Tk plus 1. Taking k equal to n minus 1, we have a path alpha tilde in x tilde defined on I which lifts the given path alpha in capital X such that alpha tilde 0 is equal to x0 tilde. The uniqueness of the lift follows from a lemma that we have discussed before. So, we have seen that given a path in a topological space, we can always construct a path in its covering space. Not only that, if we fix a point in the fiber of the initial point of that path in the covering space, then that path can be lifted uniquely to a path in a covering space having that fixed point as the initial point of the path. Now we shall see that homotopy also has a similar type of property. We state homotopy lifting theorem for a covering map. Let P be a covering map from x tilde to x such that P of x 0 tilde is equal to x 0. Let Y be a topological space and small y 0 is a point taken from capital Y. If f tilde from y to x tilde has the property that it takes y 0 to x 0 tilde and it lifts f from y to x, and H is a homotopy with h y 0 equal to f y for all y belonging to capital Y, then there exists a homotopy H tilde such that H tilde y 0 is equal to f tilde of y. Now we have to define a continuous function H tilde such that P composed H tilde is equal to H and H tilde y 0 is f tilde y for all y belonging to capital Y. So we define this H tilde in 3 steps. Step 1 is that we take a point y from capital Y. Since P is a covering map, for each t there exists an admissible neighborhood ut of h y t in capital X, and as h is continuous and ut is open in capital X, H inverse ut is an open neighborhood of the point yt. There exists a basic open set At cross Bt such that yt and H inverse ut contains that basic open set At cross Bt. Then we collect all these sets Bt such that T varies over the closed interval 0 1. Then this collection forms an open cover of capital I, that is the closed interval 0 1. Now capital I is compact. So there are finitely many points I is equal to 0 to n minus 1 such that capital I is union of Bti. Without loss of generality, we assume that these points are in the order. That means T0 is less than T1, less than T2 and so on. So we define Vy as the intersection At0 intersection At1 intersection with Atn. Then for y belonging to capital Y, there exists an open neighborhood Vy and a partition of the closed interval 0 1 such that capital H operated on Vy cross the closed interval Ti Ti plus 1 is contained in Ut for all I. Now the step 2 is that using a similar inductive argument as in path lifting property, for each y belonging to capital Y, we get a continuous function capital Hy tilde from Vy cross I to x tilde such that P composed Hy tilde is H restricted to Vy cross I and Hy tilde evaluated at the point z0 is equal to f tilde z for all z belonging to Vy. Now in step 3, we take Yt from the pair Yt from Vy1 cross I intersection with Vy2 cross I. Then Yt belongs to Vy1 cross I implies that there is a continuous function Hy1 tilde from singleton y cross capital I to x tilde such that P composed hy1 tilde equal to h restricted to the singleton y cross I, and hy1 tilde evaluated at the point y0 is equal to f tilde of y. On the other hand, the pair yt belongs to vy2 cross I, which implies that there is a continuous function hy2 tilde from the singleton y cross I to x tilde such that P composed hy2 tilde equal to h restricted to singleton y cross I and h y2 tilde evaluated at the point y0 is equal to f tilde of y. So, by the uniqueness of path lifting, hy1 tilde yt must be the same as hy2 tilde at the point yt. Hence, the value of hy tilde at the point yt does not depend on the choice of vy. Therefore, combining these functions, we define a function h tilde from y cross I to x tilde given by h tilde yt is equal to hy yt. Now, we want to show that this h tilde is continuous. We take an open set U subset of x tilde, then h tilde inverse of U is the union of hy tilde inverse of U where y varies over the set U. For each y, hy tilde from vy cross I to x tilde is continuous, which implies that hy tilde inverse of U is open in vy cross I. Since vy cross I is open in y cross I, hy tilde inverse of U is open in h tilde inverse of U. So, h tilde inverse of U being a union of open sets must be open. That is, h tilde is a continuous function such that h tilde lifts the given function capital H. Now, we have the corollary of homotopy lifting property, that suppose we start with a covering projection P, sigma and tau are paths from x0 to x1 such that sigma is path homotopic to tau, sigma tilde and tau tilde are lifts of sigma and tau respectively, both beginning at x0 tilde. Then the result says that sigma tilde 1 is equal to tau tilde 1 and sigma tilde is path homotopic to tau tilde. We get another corollary that whenever P is a covering projection, the corresponding induced homomorphism P sharp from the fundamental group of x tilde taking x0 tilde as the base point to the fundamental group of x taking x0 as the base point is a monomorphism. So, before we conclude, we point out that if we start with a loop in the base space, then its lift may not be a loop. For example, let us take the function alpha from R to S1 given by alpha t equal to cos 2 pi t sin 2 pi t. Then of course, it is a loop in S1, but its lift is a line segment. With this, we end module 2 of chapter 7.